Welcome to TalkTensors. Imagine training a martial artist for like 10,000 hours.
Right.
And they are just terrible. Like they can't land a single punch in a real sparring match.
They're just rigidly going through the motions.
Yeah, exactly. They look stiff, they're awkwardly repeating the exact footwork you showed them, and they just collapse the second an opponent does something unexpected.
Which is, normally when you'd fire the coach.
Right. Traditional coaching logic says you fire the coach or you tell the student to find a new career. But what if you just ignored that?
What if you kept going?
Yeah, what if you locked them in the gym and kept training them for another 50,000 hours, and suddenly, literally overnight with no warning, they become a grandmaster?
It sounds totally absurd.
Yeah, it sounds like a terrible sports movie script.
Yeah.
But they start anticipating moves they've never seen, flowing like water, and that exact phenomenon is happening right now inside artificial intelligence.
It really defies almost everything we thought we knew about how learning works, both in humans and in silicon.
Yeah.
We have this deeply ingrained assumption in computer science that if a system isn't improving after a certain point, it's just, it's peaked.
You're just wasting electricity at that point.
Exactly. But we are discovering that the most profound breakthroughs in machine intelligence don't happen smoothly. They happen in these sudden, violent leaps of comprehension long after you thought the model was just brain dead.
If you are a graduate student pulling your hair out over your latest neural network build, or just someone trying to keep up with the bleeding edge of tech without drowning in 50-page academic preprints, you are in the right place. Today, we are taking a massive deep dive into a debate that is absolutely tearing up the timelines on Hacker News and AI research forums right now.
It is everywhere.
It really is. We are asking the defining question of our generation. Are large language models actually reasoning, like truly internalizing logic? Or are they just, incredibly convincing stochastic parrots that have memorized the statistical patterns of the entire internet?
And that phrase, stochastic parrot, has really become the ultimate insult in the AI community.
Oh, for sure.
And for good reason. Because if these trillion parameter models are just stochastic parrots, there is a hard mathematical ceiling on what this technology can ever actually achieve.
Right. A parrot can recite the Constitution, but it can't write a new law.
Precisely. If they are just mimicking, we will never reach true general intelligence. But if they are reasoning, if they are capable of abstracting pure logic from raw data, then the sky isn't even the limit.
I want to cut right through the noise today. We are exploring a paradigm shift that suggests transformers, the architecture behind almost every major AI you use today, from ChatGPT to Claude, are in fact entirely capable of implicit reasoning.
They really are.
They can internalize complex logic without you having to hold their hand and prompt them step by step. But this capability is only unlocked through that martial arts analogy I mentioned earlier. It's a deeply fascinating, counterintuitive phenomenon called grokking.
Grokking requires pushing past a boundary that most machine learning engineers are honestly terrified of.
Yeah.
It involves training a model far, far beyond the point of what we call overfitting into a completely uncharted regime of generalization.
We have a massive amount of ground to cover in this conversation. We're going to break down the actual mechanics of this grokking phenomenon.
Yeah.
We're going to use mechanistic interpretability, which is basically neurosurgery, for code to peer inside the black box of the transformer layers.
We'll actually look at the exact circuits forming in the artificial brain.
Right. We'll explore why these models fail so spectacularly at some logical tasks, but succeed flawlessly at others. And we're going to culminate with this staggering benchmark, where a tiny, highly trained model goes head-to-head with behemoths like GPT-4 and Gemini.
And it absolutely wipes the floor with them.
It is a complete David and Goliath scenario, and the implications for how we build the next generation of AI are massive. So, okay, before we get at the giant slaying, we need to establish the battlefield. Why is this specific debate about implicit reasoning dominating the conversation right now?
Well, to understand that, I think we have to look at the current state of the art and a very specific frustration every developer is facing right now.
Okay.
We need to distinguish between two types of memory. You've got parametric memory and non-parametric memory.
Okay, let me take a swing at defining these, and you tell me where I'm off.
Go for it.
Parametric memory is the knowledge that is literally baked into the neural network during its massive multi-million-dollar training run.
Yes.
It's the billions of weights and biases. It is the model's internal worldview. So when I ask a model, what is the capital of France? And it instantly outputs Paris without looking anything up, it is relying on parametric memory. It's muscle memory. It's intuition.
Exactly.
Non-parametric memory, on the other hand, is like an open book exam. It's knowledge retrieved into the model's context window at runtime. This is what everyone calls retrieval augmented generation.
Like the current industry obsession.
Yeah, it's when the model searches a database, pulls a PDF into its prompt, reads it, and then gives you an answer based on that text.
That is a highly accurate breakdown. And to add a bit of technical flavor to your parametric memory definition, those weights and matrices of floating point numbers are notoriously rigid.
They're locked in.
Once the training run is over, yeah, those numbers are locked in. You can't just easily go in with a scalpel and change the matrix to update a single fact without risking catastrophic forgetting across the rest of the network.
Which is exactly why the entire industry trend lately has been leaning heavily into non-parametric memory. Everywhere you look, the advice is just use RAG.
Oh, absolutely.
Don't try to teach the model everything, just teach it to read well and give it a search engine. Why? Because updating parametric memory is hard, models hallucinate when they guess, and most importantly, models suffer from a fundamental flaw called the compositionality gap.
The compositionality gap. This is the crux of the stochastic parrot argument.
Right.
It describes a phenomenon where a neural network has perfectly memorized, isolated individual facts, but completely fails to implicitly connect them together to form a new logical conclusion.
Yeah. Let's ground this. I've seen the classic Barack and Michelle Obama example used in the research to demonstrate this. Let's walk through that because I think it perfectly illustrates how bizarre alien intelligence can be compared to human intelligence.
It is a perfect example. So during its massive training run across the internet, a language model will encounter the fact Barack's wife is Michelle millions of times.
Sure.
It memorizes that perfectly. It's locked into the parametric memory. It will also encounter the standalone fact Michelle was born in 1964 millions of times. It memorizes that perfectly too.
So fact A to B is rock solid. Fact B to C is rock solid.
But if you open a fresh prompt and ask that same model, when was Barack's wife born? It will often stumble.
Really?
Yeah, it might hallucinate a random year, it might say it doesn't know, or it might get it right, but only after wandering through a total unrelated tangent. It possesses the atomic facts, but it lacks the native ability to robustly compose them into the inferred fact that Barack's wife was born in 1964.
Unless you explicitly force it to spell out the steps.
Exactly.
That's what chain of thought prompting is. You have to treat this trillion parameter supercomputer like a toddler and say, first, identify Barack's wife. Second, find her birth year, and then it gets it right.
Which is incredibly frustrating.
It drives me crazy. It's like cramming for an exam using flashcards.
Yeah.
You memorize the definition of mitochondria as the powerhouse of the cell. You memorize the definition of ATP as cellular energy. But if the professor combines those two concepts into a single trick question on the final, you just freeze.
Right.
You freeze because you haven't actually understood the underlying biological relationship. You've just memorized isolated strings of text.
You've nailed the human equivalent.
Yeah.
The model has mapped the statistical proximity of words, but it hasn't built a conceptual logical graph of how those concepts interact in a three-dimensional reality.
So here's my question. Is implicit reasoning the ability to just know the answer without writing out a step-by-step proof in the chat window fundamentally doomed by the transformer architecture? Are these models inherently incapable of doing this internally, or are we just training them wrong?
Because if they can't do it, true artificial general intelligence is a pipe dream.
Exactly.
And it's worse than a pipe dream. It makes our current systems fundamentally unscalable. Let's look at the systemic cost of the compositionality gap. If a model truly cannot implicitly reason, then it is forced to store knowledge redundantly to be useful.
What do you mean?
Well, it has to explicitly memorize Barack's wife is Michelle, and Michelle was born in 1964, and Barack's wife is born in 1964 as three completely separate, unconnected strings of trivia.
Oh, wow. That sounds like a horribly inefficient use of billions of parameters.
It is a catastrophic waste of compute, and it makes updating the model's worldview a complete nightmare.
Right, because if something changes.
Exactly. Imagine a real-world scenario where a fact changes. Say, a CEO steps down and a new one takes over. In a system capable of implicit reasoning, you would just update the single foundational atomic fact. Company X's CEO is now person Y.
And the model would logically deduce all the downstream implications of that change automatically.
But without reasoning, you have to find and update every single redundant, composed variation of that fact scattered across the internet and the training data. Person Y's new salary, person Y's new parking spot. Company X's new leadership direction.
It's impossible.
It fundamentally impedes systematic generalization.
Okay, so the stakes are incredibly high. To answer whether transformers are permanently doomed or just train poorly, we have to isolate the problem. But we can't test this cleanly on models like ChatGPT or Claude because they are trained on the open internet.
And the internet is messy.
It's totally uncontrolled. If ChatGPT gets the Brock's wife question right today, we have no idea if it actually reasoned through the two hops in its head, or if it just happened to ingest a specific BuzzFeed article that explicitly contained the sentence, Brock's wife, born in 1964, wore a blue dress.
You cannot perform rigorous science in a contaminated environment.
Right.
We can't definitively prove a model is reasoning if there is even a fractional percentage chance it just memorized the final answer from a random Reddit comment. To truly study implicit reasoning, we need a pristine laboratory.
We need absolute control.
Yes, we need an environment where we have godlike knowledge of exactly what data the model has seen and what data it has never seen.
So we have to play God and build a synthetic universe. Let's dive into the methodology of the experimental sandbox used to prove this grokking phenomenon. We aren't using English test here, right? We are creating a pure, abstracted knowledge graph.
That's right. Imagine a pristine, closed universe consisting of exactly 2,000 distinct entities. For a human, you could think of these as 2,000 different people in a massive royal family tree.
Okay.
But for the model, they're just abstract, meaningless tokens.
Yep.
Entity 1 through entity 2,000. And connecting these entities, we define exactly 200 possible relations.
So we have entities and relations. We are basically building a massive web of connections. And the beauty of this is that the researchers break the training data down into two very distinct, highly controlled buckets: atomic facts and inferred facts.
Let's establish these because this division is the foundation of everything that follows.
Okay, lay it out for me.
Let's start with atomic facts. These are the basic ground truth statements of our synthetic universe. You could think of them as the absolute axioms in a formal mathematical system. They always take the form of a simple triplet: subject, relation, object.
Like entity A has relation 1 with entity B.
Exactly. Sticking to our royal family analogy, an atomic fact would be Charles is the father of William.
Right.
It's just a raw single hop data point, the raw flashcards.
Got it. And the second bucket.
Then we have the inferred facts. These are the deductions or the theorems. They're not random. They are generated directly from the atomic facts using a set of strictly defined, hidden, latent rules.
Give me an example of how a rule generates an inferred fact.
Let's say we have the atomic fact A relates to B and another atomic fact B relates to C. We might program a latent rule into the universe that dictates. Anytime A relates to B and B relates to C, it is a universal truth that A relates to C.
Okay, so that final deduction, A relates to C, is an inferred fact.
Yes. Back to the royals, Charles is the father of William. William is the father of George. The latent rule is the concept of a grandfather. Therefore, the inferred fact is Charles is the grandfather of George.
It's a perfect mapping. Now here's where the rigorous science comes in. To actually evaluate if the neural network is learning to reason, meaning, is it actually discovering that latent grandfather rule, or is it just memorizing the final string, Charles is the grandfather of George? We need to implement a strict quarantine.
Right. We need to talk about in-distribution data versus out-of-distribution data. ID versus ODE. This is where we test what researchers call systematicity.
This is the most crucial part of the setup. Let me see if I have this right. We take our total pool of those basic atomic facts, those axioms, and we split them. We take 95% of the entities and their relations, and we put them in one pile. That's our in-distribution or ID set.
Correct.
We feed the model all of these ID atomic facts, but we don't just give it the raw facts. We also give it a random portion of the inferred facts, the theorems that were deduced only from that ID set.
That's it, exactly. So the model sees the raw facts, and it sees some examples of how those facts combine according to the hidden rules. It sees Charles is father of William. William is father of George, and it also sees the answer key for that specific pairing. Charles is grandfather of George.
Okay, so the first test is in-distribution evaluation. We test the model on the ID inferred facts that we held back during training. We basically ask it, okay, you know Charles, William, and George, you know the rules, but what about this other family branch? Can you correctly deduce this new combination that you haven't explicitly seen before?
And if it succeeds at that ID evaluation, it's a good sign. It means it figured out the rule for the entities it is familiar with. But scientifically, that is not enough to prove true reasoning.
Right, because it might have just learned a highly specific, localized pattern. It might think the grandfather rule only applies to people who live in London because it hasn't truly abstracted the math. It's just doing complex pattern matching.
Exactly. The ultimate test of true reasoning systematicity is whether the model can apply the learned rules to entirely unseen combinations. This is where we bring in the out-of-distribution or ODE evaluation. Remember that 5% of atomic facts we quarantine?
Yes, the completely hidden pile.
During the massive training run, the model only ever sees these ODE entities as raw, standalone atomic facts. It never sees them combined into inferred facts. It never sees them used in a deduction.
It never sees an example of an ODE entity acting as a grandfather.
Never. In the final ODE evaluation, we ask the model to apply the reasoning rules to these isolated quarantined entities.
We force it to bridge the gap completely on its own.
If it can do that, it proves it hasn't just memorized entity-specific patterns. It proves it has abstracted the pure logical rule itself, the literal mathematical concept of transitivity, and can apply it universally to any token you hand it.
It's the difference between a kid learning how to solve 2 + 2 = 4 because they memorized that specific flashcard versus a kid actually learning the abstract concept of addition, meaning they can solve x + y regardless of what numbers you substitute for the variables.
Exactly.
Okay, for the tech enthusiasts listening, let's quickly note the model specs used for this sandbox because I think it's important to realize we aren't talking about a massive Google-scale cluster here.
No, not at all. This is not a trillion-parameter behemoth. This is a highly controlled experiment. We're looking at a standard decoder-only transformer, very similar to the architecture of the original GPT-2.
So pretty small.
Incredibly small by today's standards. Just 8 layers, 768 hidden dimensions, and 12 attention heads.
Basically something you could run on a decent gaming laptop.
Pretty much.
So what happens when we train this tiny model in our pristine, highly controlled universe? Because this is where the standard machine learning playbook, the absolute gospel of data science, gets completely thrown out the window. This is the breakthrough. Let's talk about the phenomenon of grokking.
What happens here challenges everything we thought we knew about optimization and when to stop training a neural network.
Okay, picture this. You are an engineer monitoring the training run. You are watching the loss curve go down. You are watching the accuracy go up. At around 14,000 optimization steps, the model hits 99% accuracy on the training data.
It has memorized all the atomic facts perfectly.
And it has memorized the inferred facts, you showed it perfectly, is acing the test you gave it to study.
At this exact moment, traditional machine learning wisdom is screaming at you with flashing red lights. Stop training, you have converged. If you keep going, you are just going to overfit to the training data. You'll ruin the model's ability to generalize to new things because it will just rigidly obsess over the data it already has.
Right. If you actually pause the training right at that 14,000 step mark and tests generalization, testing its ability to deduce unseen in-distribution facts, it is absolutely abysmal. It gets a dismal 9.2% accuracy.
It has learned nothing about the underlying logical rules. It's just a stochastic parrot reciting the training set.
But what if you ignore the conventional wisdom? What if you ignore the red lights, ignore the textbooks, and just keep the GPUs running at full blast?
If you keep training, and we're not talking about a little bit longer, we're talking about training up to 50 times longer than it took to achieve that initial 99% training accuracy, something magical happens.
50 times longer.
Yeah. For thousands and thousands and thousands of steps, the test accuracy remains flatline at 9%. The model seems completely dead. It looks like a massive waste of compute.
But then,
suddenly, an inflection point occurs on the graph. The generalization accuracy on unseen ID facts skyrockets almost vertically. It shoots up from 9.2% to near perfect 99% accuracy.
it is just mind-bending to look at the charts. The model was basically overfit for weeks of compute time, blindly repeating itself, and then suddenly it wakes up. It achieves enlightenment. It completely understands the rules of the universe.
It perfectly maps back to that martial artist analogy you used.
Right. For the first few thousand punches, the student's brain is just executing a stiff mechanical script. It's rote memorization. But eventually, if you push far, far past the point of mechanical repetition, past the point of exhaustion and boredom, something in the nervous system clicks.
The movement grokes.
It stops being a conscious effort and becomes pure muscle memory, abstractly integrated into their body, allowing them to adapt that punch to any opponent seamlessly without thinking. The model transitions from rote memorization to abstract comprehension.
That is a phenomenal way to conceptualize it. In the terminology of mechanistic interpretability, the model physically transitions its internal wiring from a memorization circuit to a generalization circuit.
Okay, but this brings us to an incredibly important debate, and it overturns a major misconception that has been circulating wildly on social media regarding how you actually trigger this grokking event.
Oh yes. The scale is all you need crowd.
Let's get into the critical data size debate, because a lot of people are completely misinterpreting how to force models to reason.
For a while, the prevailing theory in the AI community was that grokking is triggered by reaching a critical data size, or CDS. The argument was pure brute force. If you just give the model enough raw data, eventually the sheer volume of information overwhelms its capacity to memorize.
Makes sense on the surface.
The model is forced to abandon memorization and figure out the underlying rules simply because it runs out of hard drive space in its parameters to store every individual fact.
Just scale it, throw more internet tokens at it, build a bigger data center.
It's the brute force mantra of modern AI development.
Exactly. It's an alluringly simple philosophy. But these controlled experiments in our synthetic sandbox prove that hypothesis definitively mathematically wrong when it comes to implicit reasoning. How did they prove it?
The researchers conducted a brilliant stress test. They took the ratio of inferred facts to atomic facts, the ratio of theorems to axioms, let's call that ratio of phi. They held phi constant at, say, 9.0.
Meaning for every one raw atomic fact, there are exactly 9 deduced theorems in the training data.
Right. Then they massively scaled the total volume of the universe. They increased the entity count from 2,000 to 5,000, and then all the way up to 10,000 entities.
So the absolute volume of data the model has to process is increasing drastically. If critical data size is the key, grokking should happen much faster, or at least more robustly, with the massive 10,000 entity data set. The sheer weight of the data should crush it into reasoning.
But it doesn't. When they scaled the total entity count while keeping the ratio constant, the speed of grokking did not change at all. The learning curves looked practically identical. Scaling the raw size of the data did absolutely nothing to accelerate the onset of implicit reasoning.
Wow, so it's not the size of the data that matters. It's not about reading more books. It's the distribution of the information inside the books.
It is entirely about the critical data distribution. When the researchers altered the experiment to increase that ratio phi, meaning they provided a higher density of complex theorems relative to basic axioms, pushing phi up to values like 12.6 or 18.0, that is what drastically accelerated the grokking inflection point.
Interesting.
A higher ratio of complex inferred facts to simple atomic facts forces the model to generalize much, much faster.
Okay, this is where we have to pause and dig into the physics of the optimization landscape. Why does changing the ratio, but not the overall size, force the model to wake up and learn the rules? What is actually happening under the hood?
Right.
You mentioned a specific mechanism in your notes before we started recording, weight decay. I glossed over it earlier when listing the model specs. Let's not gloss over it. What is weight decay doing to the math? Because it sounds like the model is deliberately forgetting things.
It is one of the most elegant concepts in machine learning. Let's connect this to the bigger picture of how neural networks actually learn. During training, the optimization algorithm, in this case, gradient descent, is essentially searching a massive mathematical landscape for a circuit that successfully maps the input to the correct output.
Okay.
Early on in training, the absolute easiest, laziest circuit to find is a brute force memorization circuit. It just built a massive dumb lookup table in its weights. If input is X, output is Y. It doesn't care about logic, it just maps A to B.
It's fast to learn, but it takes up a massive amount of space or mathematical complexity in the model's parameters. It's like building a separate, unique road from your house to every single grocery store, rather than just building one highway that connects to them all.
That's a great visualization.
Huh.
But there is also a generalization circuit hiding somewhere in that mathematical landscape. This circuit is elegant. It learns the actual rule. It is much more computationally efficient because it doesn't need to store every single answer. It just stores the abstract rule and calculates the answer on the fly.
Okay, so if the generalization circuit is so much better and more efficient, why does the model stay stuck in the dumb memorization circuit for 50 times longer than it needs to? And how does the ratio of facts fix it?
Because the generalization circuit is much harder to discover initially. It requires a specific combination of weights that is hard to stumble upon. But here is the key. We are using weight decay during training.
And what does that do?
Weight decay acts as a continuous mathematical penalty. Think of the model's parameters like a budget, and weight decay is an aggressive tax on complexity. It constantly penalizes the model for having large, sprawling, complex weights. It acts as a continuous evolutionary pressure, forcing the model to seek simpler, more elegant representations.
Oh, I see. So it's like a minimalist coach. The memorization circuit is computationally expensive and sprawling under weight decay.
Exactly. Now consider our ratio phi. If the ratio of inferred facts to atomic facts is low, the memorization circuit isn't actually that big, so the weight decay penalty isn't strong enough to force the model to abandon it. The model just pays the small tax and keeps its dumb lookup table.
Right.
But as you increase that ratio, as you flood the model with a massive density of deduced theorems relative to axioms, the memorization circuit has to grow exponentially larger to memorize all of those complex combinations. It becomes massively inefficient. The weight decay tax becomes absolutely agonizing for the model.
And so the optimization process, trying to minimize its loss and avoid the tax, is literally forced to discover the leaner, more elegant generalization circuit just to relieve the pressure of the weight decay.
That's it, exactly.
That is beautiful. It's not about feeding the model more raw data. It's about engineering the data distribution to make rote memorization mathematically painful, forcing the transition to abstract reasoning.
It is a triumph of optimization physics. And this isn't just theory or speculation based on looking at a line graph. We can actually prove this transition is happening physically inside the model by cracking open the neural network and looking inside.
Okay, let's go there. Mechanistic interpretability. This is where it gets really, really interesting. We know grokking works for reasoning. We see the accuracy spike. But how do we actually prove the model isn't just finding a more sophisticated way to fake it?
Right. How is it actually doing it?
For years, neural networks have been treated as impenetrable black boxes. You put data in, magic comes out, and no one knows why. But now we have the tools to perform a sort of cognitive autopsy while the model is actively thinking.
Mechanistic interpretability is completely revolutionizing our understanding of artificial intelligence.
Yeah.
Instead of just looking at the final output, we're looking at the intermediate hidden states, the actual electrical firings, the activations of the artificial neurons across the different layers of the transformer as the data moves through it. To do this, researchers rely on two incredibly powerful tools: the logit lens and causal tracing.
I was reading up on the logit lens tool before this conversation. Let me try an analogy and see if I'm understanding it correctly.
Okay.
Imagine the transformer as an assembly line bakery with 8 stations representing its 8 layers. At the very end of the line, the model outputs a fully baked cake, which is then passed through an interpreter to tell us what kind of cake it is, chocolate, vanilla, whatever. That interpreter is the output embedding matrix that turns math back into English tokens.
How it works?
The logit lens is basically asking, what if we pull the batter off the assembly line halfway through? What if we take the raw intermediate math from layer 4 and prematurely force it through the output embedding matrix?
Yeah, you're peaking early.
It's like yanking the cake out of the oven halfway through baking and tasting it to see if it tastes like chocolate yet. It allows us to see what concepts the model is currently prioritizing or thinking about at that specific layer before it has finished processing the full thought. Is that accurate?
That is highly accurate. It translates intermediate vector math into human interpretable concepts. You can literally watch a concept form layer by layer. The second tool is causal tracing. The logit lens shows us what the model is thinking, but causal tracing shows us which thoughts actually influence the final decision.
I love this part. This is where it gets into literal neurosurgery on the matrix. Explain how we trace causality.
It involves a 3-step intervention. First, you run a normal prompt through the model and meticulously record all the internal activations at every single neuron. Let's use our composition task. Fact 1, A relates to B. Fact 2, B relates to C. What is the relation of A to C? The model confidently predicts C.
Okay, normal baseline run.
The second, you run a corrupted, perturbed version of that prompt.
Yeah.
You deliberately introduce noise or change the input so the model gets confused and predicts something else.
You essentially scramble its brain.
Yes. Finally, the intervention. You run the normal, clean prompt again, but this time, right in the middle of the processing, you forcefully inject a recorded activation from the corrupted run into a specific neuron or layer.
You essentially implant a false, scrambled memory mid-thought.
Exactly. If the model's final output suddenly changes to the wrong answer, you have proven a definitive causal link. You know that specific neuron at that specific layer is causally responsible for that exact part of the reasoning process.
That is wild. We are probing the artificial brain with a scalpel. So what did the researchers find when they used the logit lens and causal tracing on this specific grokking transformer? What does the artificial brain look like before and after the big aha moment?
The findings are stunning. They mapped out the exact computational pathways, the physical circuits. Let's look at the model before grokking, when it is stuck in the 9% accuracy phase, relying on the memorization circuit.
The brute force high tax phase.
Right. When they traced the causality before grokking, it was a structural mess. The model was taking the prompt, and in the very first few layers, it was just directly associating the input tokens with the final answer based on statistical proximity.
Just guessing based on patterns?
It wasn't retrieving the intermediate atomic fact. It wasn't looking for entity B to logically connect A and C. It had just built a massive, shallow, disorganized lookup table. It was completely ignoring the logical rules of the universe.
But then we look at the model after the grokking inflection point. The extended training has finished. The weight decay has successfully crushed the memorization circuit out of existence. What does the new generalization circuit look like?
It forms a highly structured, elegant, almost beautiful computational graph. The transformer physically divides the labor of logic across its depth. In the lower layers, specifically layers 0 through 5, the model uses the input to retrieve the first atomic fact.
It finds the bridge entity.
Exactly. If the question is about A's relation to C, the lower layers fetch the fact that A connects to B. Using the logit lens, you can literally see the model holding the concept of entity B in its memory right at layer 5.
It's storing the intermediate variable. It's doing scratchpad math in its own layers.
Yes. Then, in the upper layers, layers 5 through 8, it takes that intermediate variable, entity B, retrieves the second atomic fact, that B connects to C, and computes the final target, C. It is executing a perfect two-step algorithmic deduction, physically mapped across the vertical depth of the neural network.
That is just incredible to visualize. We can conclusively prove without a shadow of a doubt that the model shifted from a giant dumb statistical lookup table to a multi-step algorithmic processor.
And this loops back perfectly to why grokking happens. As we discussed, that deep multi-layer algorithmic circuit is mathematically leaner than the giant lookup table. Gradient descent and weight decay eventually push the network into discovering this beautiful, highly structured reality.
It is a triumph of optimization. We have forced a machine to invent logic. However, this is where I have to deliver some sobering news.
Right.
This beautiful discovery comes with a massive structural caveat that threatens the entire current paradigm of AI development.
We need to talk about the tale of two tasks. We have definitively proven that grokking solves in distribution reasoning. The model learns the rules for the data it's familiar with, but the ultimate test was systematicity.
What happens when we hit it with the out-of-distribution data? The quarantined entities it has never seen used in a theorem.
This is where we see a fascinating, almost paradoxical split in the model's capabilities. The researchers tested the Grokked transformer on two different types of ODE reasoning tasks, composition and comparison. And the results were diametrically opposed.
Let me guess, one worked and one didn't.
While grokking solves ID reasoning for both tasks perfectly, it completely spectacularly fails at ODE generalization for composition tasks. But surprisingly, it works flawlessly for ODE comparison tasks.
Okay, we need to deeply dissect this. Why the massive discrepancy? Let's dive into the composition failure first, because this is the holy grail of reasoning. What exactly is a composition task in this specific context? Let's stick to our example so we don't get lost in the algebra.
We've been using it as our primary example. Composition is chaining facts together sequentially. The formal rule is a two-hop sequence, the Barak to Michel to 1964 pipeline.
Right.
We know the model grokks this beautifully for in-distribution data. We just saw the beautiful circuit. The lower layers fetch the first hop, Barak to Michel, and store Michel as the bridge entity. The upper layers then fetch the second hop, Michel to 1964, and output the target year.
So why does this elegant, logically sound circuit completely crash and burn when we feed it out of distribution entities? If it knows the rule, why can't it apply it?
It comes down to a fundamental structural bottleneck in the vanilla transformer architecture itself. It's not a failure to the model's logic, it's a failure of its hardware design. Let's think about how that generalization circuit actually stores information across its layers.
Okay.
The transformer does not have a centralized global database, a hard drive that every layer can access equally. It processes sequentially, strictly feed-forward.
Information flows in one direction. Layer 1 feeds to layer 2 feeds to layer 3, and so on. It never loops back. It can't look behind itself.
Precisely. Because it lacks recurrence, the ability to share memory backwards or across layers dynamically, the model is forced into a highly inefficient workaround during the training process to make the two-hop circuit work.
What kind of workaround?
To execute that sequential composition circuit, the model literally has to create two separate copies of the atomic facts in its parameter weights.
Wait, what? It memorizes everything twice? That seems incredibly inefficient for a system trying to minimize weight decay.
It has no choice. It stores one copy of the atomic facts in the lower layers to handle the first hop of the deduction, and it has to store a completely separate redundant copy of the exact same atomic facts in the upper layers to handle the second hop, because the upper layers can't reach down into the lower layers to ask for a fact they need.
Okay, I see exactly where this is going, and it is a fatal flaw for the ode data. Let's trace the Barack and Michelle example, assuming they were our quarantined ode entities.
Let's do that. Think about the outer distribution data. By definition, the quarantined OD entities were only ever shown to the model during training as isolated, standalone atomic facts. They were never shown as the second step of a composed theorem.
Oh, wow. So because Michelle only appeared as a basic first hop fact during training, the optimization process only bothered to store her birth year in the lower layers.
Exactly.
The model never had an incentive to create that second duplicate copy of Michelle born in 1964 in the upper layers because it never needed her for a second hop during its training regimen.
You've got it perfectly. So during ode evaluation, we give it the prompt. The model starts the reasoning process perfectly. The lower layers successfully retrieve the OB first hop. Barack's wife is Michelle.
They successfully identify the bridge entity, Michelle. They hold her in layer 5.
But then they pass that bridge entity to the upper layers to finish the deduction. And
the upper layers are empty. The facts aren't there. The upper layers query their local memory for the second OD hop Michelle's birth year and find absolutely nothing.
The whole reasoning chain collapses.
The model fails systematically, not because it didn't learn the logical rule of composition, but because the strict feed-forward architecture forced an artificial memory partition that hid the necessary data from the layers that needed to compute it.
It is a profound insight into the limitations of our current technology. The vanilla transformer isn't necessarily bad at reasoning. Its strict sequential architecture forces it to silo its knowledge, creating literal physical blind spots for novel sequential tasks.
That is the tragedy of composition. It's heartbreakingly close to intelligence, thwarted by filing cabinet design. But you said comparison succeeds at ode. How is that possible? If the architecture is fundamentally siloed and flawed, why does comparing things work flawlessly?
Because comparing two facts doesn't inherently require a sequence of dependent hops. It requires parallel retrieval. Let's define the comparison task. Here we are evaluating parallel attributes.
Okay.
The rule is, if entity 1 has attribute A with value 1, and entity 2 has attribute A with value 2, and value 1 is less than value 2, then entity 1 is less than entity 2.
So a simple real-world example. If John is 30 years old and Mark is 40 years old, John is younger than Mark.
Yes. Now, let's use our mechanistic interpretability tools to look at the generalization circuit the model discovers for this specific task during the grokking phase. It is entirely different from the composition circuit.
How does it structure the logic differently?
Because comparison isn't dependent on finding a bridge entity first, the model discovers a parallel circuit. Using the logit lens, we see that the model retrieves the attribute values for both entity 1 and entity 2 simultaneously, in parallel, entirely within the lower layers. At layer 5, the model is holding both John's age and Mark's age at the exact same time.
They are retrieved side by side in the same physical region of the network, the lower filing cabinet.
Exactly. Then it passes both those values up to the upper layers. The upper layers in this circuit act purely as a comparative calculator. The upper layers don't need to retrieve any facts themselves. They don't query their local memory.
They just do the math.
They just run a mathematical comparison on the two values handed up to them by the lower layers and output the correct relational label, younger.
And this is the victory. Because all the fact retrieval happens in one unified place, the lower layers, there is no need for duplicate copies.
Exactly. Since all atomic facts, both ID and ode, are securely stored in those lower layers during the initial phase of training, the model can flawlessly execute the parallel retrieval. It pulls the two OD facts, say, two quarantined entities it has never compared before, passes their values to the upper layer calculator, and perfectly evaluates unseen entity comparisons. True systematic generalization is achieved.
So what does this all mean for the big picture? If we step back, you're saying the vanilla transformer, the exact architecture powering the AI revolution, the core of ChatGPT, Claude, Llama, has a fundamental structural roadblock for complex multi-step logical reasoning simply due to its lack of recurrence.
That's what the data implies, yes.
It's essentially forced to memorize the entire dictionary twice if it wants to use a word in the second half of a sentence. If we fix the architecture, do we fix the reasoning?
That is the incredibly compelling conclusion of this research. The failure isn't in the model's cognitive ability to abstract logic. It's an input-output bottleneck between its internal layers. This strongly suggests that memory-augmented architectures, or models with parameter sharing and explicit recurrence, like universal transformers, where the output of a layer physically loops back into itself, are absolutely critical for the future of robust AI reasoning.
We have to allow the layers to dynamically talk to a unified global memory bank.
Yes.
This theoretical exploration is absolutely fascinating. Peering into the layers, mapping out the duplicated memory silos, contrasting the parallel versus sequential circuits. It is incredible computer science. But I know exactly what the seasoned practitioners listening to this are thinking.
Oh, I'm sure I know too.
They're thinking, this is a pristine sandbox. This is a synthetic universe with 2,000 perfect entities. What does this actually mean for real-world deployment? How does this tiny Grokked toy model compare to the multi-trillion-dollar non-parametric behemoths currently dominating the enterprise market?
That is the ultimate test. Theory is great, but we need empirical dominance. And the researchers didn't just stop at simple two-hop comparisons. They designed a final benchmark to push the limits of both parametric and non-parametric systems to their absolute breaking point.
Let's set the stage for this ultimate showdown. They created a massively difficult, complex reasoning task. They took the comparison task we just talked about, comparing attributes, and they added the heavy mathematical rules of transitivity and symmetry.
Let's define those quickly to understand the scale of the challenge. Symmetry means if the model knows A is older than B, it must implicitly deduce that B is younger than A.
Makes sense.
Transitivity means if it knows A is older than B and B is older than C, it must deduce that A is older than C.
Sounds simple enough for a human to follow.
It is, until you realize the scale of the data. They created a massive search space. They populated the context with tens of thousands of these interconnected facts. And then they asked the models to evaluate a complex query comparing two entirely out-of-distribution entities.
Right.
To answer the query, the model can't just look up the two entities directly. It has to search through the massive haystack of data, locate a specific bridge entity that connects the first ode entity to the rest of the graph, locate another bridge entity that connects the second ode entity, and then trace a long chain of transitive and symmetric logic across the entire graph to determine their final relationship.
And crucially, there are zero surface-level semantic clues. The names of the entities don't give away their relationships. It isn't like guessing Grandpa Joe is older than Baby Tim.
Exactly.
It is pure brute force logical pathfinding through a labyrinth of 28,000 abstract facts. It's a nightmare scenario for an AI. So let's bring in the Goliaths. They tested the absolute state-of-the-art non-parametric models, GPT-4 Turbo and Gemini 1.5 Pro.
The big guns.
These models have massive context windows. They can swallow a whole textbook in one prompt. How were they tested?
They tested them using every trick in the modern ML playbook to give them the best chance. They tested them with standard massive context loading, just dumping all 28,200 facts into the prompt and asking the question.
Wow.
They also tested them using retrieval augmented generation, or R, where an external search engine narrows down the facts to the most relevant 5,000 before feeding them to the model's context window.
And they must have used intensive chain of thought prompting, right? Asking the models to think step by step, to explicitly trace the logic out loud.
They tried direct zero-shot prompting, and they tried intensive chain of thought prompting. They gave the Goliaths every possible advantage, and the results: utter catastrophic failure.
How bad are we talking? Because random guessing on this task would get you about 33% accuracy, since the answer is a multiple choice of either older, younger, or same age.
Direct prompting, chain of thought prompting, RAG, across the board, regardless of the technique, the non-parametric Goliaths hovered around 11% to 37% accuracy. They basically performed at, or significantly below, random chance.
Below random chance? How does a model as impossibly smart as GPT-4 or Gemini perform worse than a human flipping a three-sided coin?
We have to look at how they fail, because it reveals the flaw of non-parametric memory. When prompted to think step by step, you would expect them to map out the logic. But the search space is simply too complex to hold in a transient context window.
It just overloads them.
Gemini, for instance, when forced into chain of thought, became completely overwhelmed by the labyrinth. In a staggering 70% of its attempts, it gave up halfway through the reasoning chain and incorrectly concluded that the problem was unsolvable based on the provided facts. It just lost the thread.
It just threw his hands up. Too hard, can't be done. But what about the ones that did answer? Why do they hallucinate instead of just saying, I don't know, for the other 30%?
Because of their fundamental training objective. These Goliaths are ultimately next token predictors trained on human text, optimized for helpfulness.
Oh, right.
Human text rarely just stops dead in the middle of a mathematical proof and says, I give up.
Yeah.
It's statistically easier for the model to fall into a predictive groove and generate a plausible sounding lie than to admit defeat.
So it fakes it.
When the researchers analyzed the rationales where the models got the answer correct, the vast majority of time, the internal logic was completely broken. The models were hallucinating fake facts, inventing relationships that didn't exist in the prompt, just to force the math to work out to the correct final answer.
It was the illusion of reasoning. It knows what the shape of a logical proof looks like, so it just generates text that mimics a proof, regardless of whether it's actually following the rigid rules of transitivity.
Yes.
Non-parametric memory, just dumping data into the context window, completely falls apart when deep, multi-hop logical integration is required. It's like trying to learn calculus by speed reading a textbook during the exam.
Exactly. Now, enter the day with our story. The researchers took their tiny, 8-layer, fully grokked parametric transformer. It has absolutely no RAG system. It has no massive context window to look things up.
Just a small, highly trained model.
But it has been extensively trained, baked for thousands and thousands of epochs on the pure logic of the graph. It is unleashed on the exact same data set, exact same queries.
What was the result?
99.3% accuracy, near absolute perfection.
That is just unbelievable. A tiny model running on a fraction of the compute, destroying trillion parameter titans. How? Why does the parametric memory succeed so spectacularly where massive context windows fail?
What is fascinating here is the sheer power of deep parametric compression. By forcing the model to grok the training data through extended optimization and the agonizing pressure of weight decay, the parametric memory didn't just store facts like a filing cabinet. It deeply integrated the information. It internalized the global topology of the entire knowledge graph into its weights.
It built a holistic, three-dimensional map of reality in its parameters, rather than just scanning a flat list of instructions in its prompt.
Exactly. And here is the most mind-blowing detail of the entire study. The researchers looked closely at how the grokked transformer was actually solving these complex ODE queries.
Okay.
Remember, it was never explicitly trained to infer the missing attributes of out-of-distribution entities. It was only trained on ID deductions. But because it had internalized the global logic so profoundly, the model spontaneously learned to infer the hidden values of the ODE entities entirely on its own.
You're kidding.
It seamlessly integrated them into its parallel comparison circuit to output the perfect answer.
It generalized the rules of the universe so thoroughly that it basically reverse engineered the missing pieces of reality without even being asked. That is parametric supremacy in action. If you give a neural network enough time to truly digest the data, its ability to navigate complex logic infinitely surpasses a giant model trying to speed read a textbook at runtime.
It fundamentally reframes the current industry obsession with ever larger context windows and RGARE architectures. Yes, non-parametric memory is great for looking up isolated facts. If you need to know the capital of Peru, use RGARE. But for deep, integrated reasoning, for actually synthesizing new knowledge, parametric memory, when properly cultivated, is vastly superior.
Which brings us to the implications for the field. We've covered a massive amount of highly technical, theoretical ground today. Let's synthesize this for the developers, the engineers, the startup founders listening. How does this alter the trajectory of machine learning research? What are the practical takeaways we can apply to how we build models today?
I think there are three major paradigm-shifting takeaways here. First, explicit verbalization, we call chain of thought prompting, is increasingly looking like a temporary crutch. It is a highly effective crutch for current models that have weak parametric compression. But it isn't the end game of AI reasoning. If a model has truly grokked the logic, it doesn't need to talk to itself. in the chat window to find the answer. It can evaluate the logic implicitly and instantly within its own hidden layers.
So all the current research pouring into making models generate better, longer, step-by-step rationales might be a bit of a local minimum. We are training them to fake human reasoning rather than unlocking their own native implicit reasoning speed. We're teaching calculators to show their work when they don't need to. What's the second takeaway?
The second is a direct challenge to the scale is all you need philosophy that dominates Silicon Valley.
Yeah.
Scaling data size blindly will not fix fundamental reasoning deficits. The experiments definitively show that simply throwing more entities at the model didn't trigger grokking. It is all about curating the distribution of the data.
The ratio of inferred facts to atomic facts, the density of the theorems versus the axioms.
Yes. Practitioners building data sets for foundation models need to stop obsessing over scraping the entire internet and focus heavily on data quality and distribution. You need to ensure the training data contains a high density of logical deductions and rule applications, not just massive dumps of raw, disconnected trivia. You have to make rote memorization mathematically expensive for the optimization algorithm by flooding it with complex combinations.
Quality and structural density over pure quantity. And the third takeaway.
The third relates to the architecture itself. The vanilla transformer has fundamental bottlenecks. We saw clearly how the lack of cross-layer memory sharing the lack of recurrence forces the model to redundantly duplicate knowledge, crippling its ability to systematically generalize on sequential composition tasks.
We have to move beyond the strictly feed-forward paradigm. If we want AI that can truly reason out of distribution across multiple sequential steps without failing, we need architectures that allow upper layers to dynamically query lower layers. Universal transformers, memory-augmented networks, dynamic routing. This is where the hardware and architecture research needs to aggressively pivot.
However, we also have to acknowledge the immense blind spots this research. This raises an important question. Can we realistically scale this intentional grokking process to the real world?
Right, because the sandbox we explored today was perfectly pristine. 2,000 perfect entities, strict mathematical rules, zero contradictions.
Exactly. Real-world knowledge on the open internet is incredibly messy. It is contradictory, it is highly ambiguous, and it is continuously updating. Grokking in a synthetic universe is one thing. Inducing these same elegant, generalizing circuits across trillions of messy, conflicting internet tokens is a monumental challenge.
There's a lot of noise.
The risk of the model grokking a false correlation, a conspiracy theory, or a deeply ingrained societal bias instead of a true logical rule is incredibly high.
It's the difference between mastering chess, where the rules of the board never change, and mastering geopolitics, where the rules change every day. But the fact that the underlying mechanism for true parametric reasoning physically exists within the transformer is a massive leap forward. Okay, it is time to shift gears. This is my absolute favorite part of the deep dive. It is time for our signature closing segment, Novel Notions.
This is where we take the solid empirical science we've just discussed and extrapolate it wildly into the future. We pitch outlandish, futuristic, but technically grounded ideas inspired by the trajectory of the technology.
And before we begin, I have to give the mandatory disclaimer. Novel Notions is entirely speculative. It is a thought experiment for entertainment purposes only. Do not base your startup Series A pitch on our late-night theories. You have been warned. Okay, what is your first novel notion based on this grokking breakthrough?
Idea number one. I call it latent sleep phases for data center AI.
Oh, I like the sound of that, like REM sleep for server farms.
That's the exact biological analog. Think about how human brains consolidate memories. We don't just constantly absorb new visual and auditory information 24/7. We have sleep phases where sensory input is completely cut off, and our brains actively replay, compress, and extract underlying logic from the day's messy experiences.
Right.
Based on what we've learned today about the absolute necessity of extended training and weight decay to force the transition from memorization to generalization, I propose that future foundation models will require mandatory, scheduled offline grokking phases.
So instead of a massive, continuous pre-training run where OpenAI or Google just shovels internet text into the GPU cluster for 6 months straight until they run out of compute budget.
Right. Instead, the training becomes rhythmic. You feed the model massive amounts of new internet data, the raw, messy atomic facts. It memorizes them rapidly using inefficient, sprawling circuits. Then you cut off the external data feed. You put the entire data center to sleep.
Fast.
During this phase, you introduce an intense, highly curated synthetic data stream derived exclusively from the model's own newly acquired knowledge. You force it to train continuously on reasoning graphs built from its own internal representations, while cranking up the weight decay to maximum penalty.
You are intentionally inducing the agonizing mathematical pressure. You are actively forcing the model to compress the messy trivia it just learned into elegant, generalized logic circuits before you let it wake up and browse the internet again. It's artificial memory consolidation that is brilliantly plausible. It solves the exact issue we just talked about regarding the real world being too messy to grok directly. You let the model memorize the mess, then you mathematically sanitize and grok the logic offline in a controlled dream state.
It could fundamentally change how we schedule compute clusters. Instead of 100% active training, it's 50% ingest, 50% consolidation. Now, what's your novel notion?
Idea number 2. I want to take that structural bottleneck we found in the composition task incredibly seriously. I call this the Ouroboros architecture.
The mythological snake eating its own tail. Fitting for a recurrent network.
We saw definitively that the vanilla transformer fails at multi-hop ode reasoning because it's strictly feed-forward. Layer 8 physically cannot ask Layer 1 for a fact it forgot to copy. It's a one-way street. We mentioned universal transformers earlier, but I think the next dominant AI architecture won't just share parameters. It will be truly dynamically recursive at runtime, scaling its depth based on the logical complexity of the prompt.
How would that actually work mechanistically without causing an infinite loop?
Imagine a massive 96-layer foundation model. For a simple comparison task, is John older than Mark? It acts normally. Data flows from layer 1 to 96, the parallel circuit fires, and the answer pops out. But for a complex 10-hop composition task navigating that 28,000 fact labyrinth, a dynamic routing mechanism detects the need for deep logical search.
Right.
The output of layer 96 isn't the final answer. Instead, it is dynamically looped back and injected as the input into layer 1, but this time carrying the intermediate bridge entities it just found as a new contextual payload.
I see. It effectively allows infinite sequential hops without requiring any redundant memory storage in the weights. The lower layers always act as the universal, perfectly accurate filing cabinet, and the upper layers always act as the pure logic processor. Every time the processor needs a new fact to continue the reasoning chain, it loops the request back down to the filing cabinet.
Exactly. The architecture becomes a true reasoning engine, an Ouroboros, looping continuously until the logical proof is completely satisfied, at which point it exits the loop and outputs the answer. It completely bypasses the feed-forward memory silo problem. It would require a total rethink of how we batch process attention matrices in GPUs, but it would unlock true systematic generalization for literally any length of logical chain.
That is a fascinating architectural vision, and it directly, surgically addresses the exact causal breakdown we traced in the mechanistic interpretability experiments today.
It's all connected. All right, we have covered a staggering amount of ground in this conversation, from stochastic parrots to pristine synthetic universes, from the magic of grokking and the minimalist coaching of weight decay to the surgical precision of the logit lens. We've seen trillion-parameter Goliaths stumble blindly in complex search spaces, and we've envisioned data centers dreaming in latent sleep phases.
It's a profound reminder that we are still in the very, very early days of understanding the alien intelligence we are actively building. The black box is only just slowly starting to crack open.
And that brings us to our final lingering thought for this deep dive. Think back to the beginning of our conversation. We talked about the desire for transparency, the frustration of the stochastic parrot argument, and the murky black box nature of these massive neural networks. We now know that deep within those billions of parameters, elegant, generalizing reasoning circuits actually can form, but only if given enough time and the right mathematical pressure to compress their knowledge. So, I leave you with this provocation. What if the massive language models we are interacting with today, the ones currently sitting on our phones, embedded in our browsers, writing our emails, already contain all the raw atomic facts required to cure major diseases, or design room temperature superconductors, or definitively solve the energy crisis? What if the knowledge is already securely inside their parameters, but they simply haven't been allowed to bake long enough to grok the connections? Maybe the true intelligence explosion we are all waiting for isn't about frantically feeding them more internet data. Maybe it's about giving them the time, the intense algorithmic pressure, and the recursive architecture to truly understand what they already know. Thank you for joining us on this deep dive. Keep questioning, keep exploring, and we will see you next time on the Deep Dive.